In this video, we're going to solve compound inequalities. Now, there's two types of these, the or the and, okay? So basically, they're pretty easy to figure out which is which. Or has the word or in it, as you can see here, in number 1. So it'll be an or inequality, so we're going to go ahead and solve that. It's really like 2 in 1, two problems in one. You're just going to solve this one, the one on the left, and then you're going to solve the one on the right, okay? In number 2, you can see this is an and inequality. It looks a little different. You can see that the variable term is in between two numbers, okay? So that's the condition. There's two conditions on that one. It has to be greater than this number and less than a number, this number, okay? So one at a time, let's go ahead and solve, and then we'll talk about what those solutions mean, and we'll also have to graph them, okay? So for this or inequality in number 1, I'm going to go ahead and solve these individually, okay? So it's, like I said, 2 problems in 1, so we'll go ahead and solve. First thing I would do, I would solve this like an inequality or an algebraic equation. The steps are the same. I would add 4 to both sides. That gives me 8x is greater than or equal to 24, and then I divide by 8, right? Didn't do anything different than if I was solving an equation. That gives me greater than or equal to 3. All right. There is one big difference when we're solving these inequalities. I'm going to show you with this example. So if this were an equation, I'd do the same work right here. I distribute negative 3x. Negative 3 times negative 4 is positive 12. Don't forget to make that a plus. That's a common mistake. All right. What do I do next? Subtract 12 from both sides. That gives me negative 3x is greater than negative 3. And then I divide by negative 3. Right. Here's the big difference now, or here's the thing that I really got to remember when I solve linear inequalities. Whenever I divide, notice I'm dividing by a negative number. Whenever you divide or multiply by a negative, it always means flip your sign, okay? Or you always have to flip your sign around. Okay, so those are my 2 solutions. So what do? We just treated those as 2 separate problems. Now I'm going to graph them as 2 separate graphs, basically, but on one number line. I got to graph x less than negative 1, and I got to graph x is greater than negative 3. So let's start with greater than or equal to 3, I should be saying. Here's 3. I'll use a bracket, right? And then I'm going to shade. Everything that's greater than or equal to 3 is represented by that shaded region. The 3's included, bracket means include, parenthesis means don't include, the endpoint, and then everything greater. So 5 is part of the solution set, 10 is part of the solution set, 3 is part of the solution set. Okay, now graph the other one, x less than 1. Find 1 right here, and here I'm using my parenthesis because 1 is not included. It's just all the values that are less than, which I am representing by that shaded region. Okay, so there's all your values less than 1. So bringing it all together, the solution to this compound inequality, this original inequality right here, are any of those shaded numbers, which is a lot, right? It's in fact an infinite amount. It goes off to infinity this way forever and down to negative this way forever. Okay, so everything in the shaded region is a solution. It can be in either this one or it can be in this one. That's the significance of the word or. It can be in either one, either or. All right? Now let's do an and. The next one is an and inequality. So this one I can kind of treat as one problem. This would be new to us. I'm going to add 5 to get x by itself. So I just have to have 5. I have to add 5 to each part of the inequality. So really there's 3 parts. Okay? So that's going to get me x by itself, which is always the goal. And I've added it to the negative 1, which is 4. I'm going to add it to the negative 8, which is negative 3. Okay, so all I did was add 5 to each part of that. And now this is an and inequality. Here's how I would read this. x is greater than or equal to -3 and also less than 4. Or another way to think about it, it's in between those two numbers. Okay, in between those two numbers. So -3 is here. I'm going to open that going to the right, the lower bound. And 4 is here. I'm going to open that going to the left. And I know I'm enclosing the solution set. So it's all the values in between are a solution to that inequality, including the endpoints. Okay. One way to check your work is you can pick a test value. Like, for example, what if x is 1? If I plug in 1 to my original inequality, right, this is where x used to be. So I plugged in 1. It should make sense. It should work out, right? So I go 1 minus 4, that's -3. And I ask myself, does this make sense? Is -3 greater than -8? Yes. Is -3 less than -1? Yes. Okay, so at least that value is right. So it kind of gives me an idea that I've done it right. Number 3 is another and inequality. So what I'll do is solve it like we did the last one. This one is just going to be a little more work. So first I distribute, just like you did before, 4x minus 2 is less than or equal to 14. I'm going to add 2 to each part of the compound inequality. So that gives me -4 is less than 4x is less than or equal to 16. And then I divide everything by 4. And that gives me my solution to my and inequality, which usually looks like this, right? It's x is kind of between two numbers, really. All right, and then I'll graph them. So the 4 opening to the left gets a bracket because of this right here. All right, that's read less than or equal to, so the 4 is part of the solution set, and a bracket indicates that. I make my brackets really big. You don't have to make them that tall. And then the -1 is right here, and that's going the other way. Okay, and it's all the values in between. Notice I use a parenthesis for -1 because the -1 is not included, but the 4 is.